Okay, so this is a featured article in Science that just appeared that talks about producing green hydrogen, the pricing of it, the challenges, the catalysts for making the electrolyzers faster and cheaper and so on. It's called the Parting of Water. Green hydrogen plant in Portollano, Spain is Europe's largest. I'm not sure exactly how it's pronounced, but I just tried my best. Green hydrogen is key to decarbonizing the world, but the costly, finicky devices that make it need dramatic improvements. So, the Sohical facility, which is owned by the Spanish company in Fresno, is owned by a Spanish company, is in Fresno, California, and they are basically using manure from 70,000 cows at the Bar 20 Dairy Ranch and put it into a covered lagoon where bacteria convert much of the cow dung into methane rich biogas, and then that's run through fuel cells to generate electricity. Fuel cells skip the step of having to produce energy, let's say by burning methane into boiling water and producing water vapor, which will run turbines, and then that will give us energy. Here fuel cells can directly take fuel like methane rich biogas and give you electricity. This is the way fuel cell cars are supposed to work, but obviously we haven't gotten very far on those either. So what happens here? So you're producing this green hydrogen only about 300 kilograms per day, which is a very tiny amount, and the plan there is to go use solar energy, which will still keep the production green, but go up to 1 ton of hydrogen per day, which will give you about 300 tons per year, let's say. And hydrogen is often touted as future of the green energy, and the allure is clear. Everybody wants to make it, but you cannot produce CO2 as exhaust, which will make it gray hydrogen. But hydrogen is useful because it is energy rich enough to drive semi-trailer trucks, cargo ships, and other heavy-duty vehicles that are tough to run on batteries. If you could use solar and wind to power up batteries and run these big monsters, then it would be easier, but you have to use hydrogen. But hydrogen is also very difficult to cool and liquefy and transport, so one imagines massive pipelines sending hydrogen from a facility to where it will be used, and so on and so forth. You also want to save emissions and energy use from fertilizer production and steel manufacturing, etc. But hydrogen does promise to be a good alternative fuel. Low carbon hydrogen is absolutely essential if we are going to address the climate crisis, says Kathy Ayers, the electrolysis expert at Nel Hydrogen, which is a Norwegian electrolyzer producer. If the Sohical is only an indication, then you know that this future of producing lots of hydrogen remains way off, long way off. According to the International Energy Agency, IEA, the world needs to churn out more than 300 million tons of green hydrogen annually if it is to have a shot at limiting global warming to 1.5 degrees by 2100. It's says 2050 here. That will be really nice. We have already crossed it, but likely we will come back anyway. But 2023 and 24 have been warm, and there is a debate about whether we crossed it. Some reprocessed data says not yet, and so on. Yet today, operating green hydrogen plants mostly in Europe and China produce just 1 million tons per year. This is a big match, says Pajares from Fresno. Production is meager. Manufacturers are producing 97 million tons of it, largely for making fertilizer and refined oil. But almost all of it actually comes from steam methane reforming, which produces, splits methane into CO2 and hydrogen. So that makes it gray hydrogen, which adds about 1 billion tons of CO2, as much emission as Japan every year. Green hydrogen comes instead from electrolyzers powered by renewable electricity, as we know, and Sohical is mentioned here. U.S. Department of Treasury finalized $3 per kilogram tax credit for producers of green hydrogen, and researchers are trying to drive down the cost of electrolyzers, of course, which account for roughly 1/3 of the cost of green hydrogen, and funding is to also boost their efficiency. The U.S. Department of Energy alone set aside $1 billion this decade to improve electrolyzer technology. The money is there, IR says. The issue is, can we actually get the systems installed? Cost of green hydrogen has already dropped over the past decade from about $10 per kilogram of hydrogen, which is like paying $10 for a gallon of gasoline, to about 5 kilograms by 2025. In 2021, DOE launched an Earthshot program aiming to drop the price to $2 per kilogram in 2026, which is right around the corner, and $1 per kilogram by 2031, at which point this will be as good as the cost of producing gray hydrogen, which means it can replace gray hydrogen and start to give us more and more green hydrogen. Among the targets of the Department of Energy, or DOE, reducing the need for costly precious metal catalysts in many electrolyzers, improving the membranes at the core of the devices to enable faster and safer hydrogen production, and finding designs that work better with the variable electricity supply from solar and wind farms. So intermittency has to be dealt with as well. There's a lot of innovation coming, says Shannon Butcher, an electrolyzer expert at the University of California, Berkeley. The trend is very similar to the march of progress in photovoltaics and wind power. Making better, cheaper electrolyzers is not the only hurdle green hydrogen faces. Butcher says hydrogen cannot be chilled and compressed easily, so it requires large pipelines and storage facilities, and powering the electrolyzers needed to make 300 million tons of hydrogen a year would require more than a terawatt of cheap renewable electricity, more than all the solar and wind currently installed worldwide. A lot of things have to come together, Butcher says. I don't know how the name is pronounced, Boettcher. I'm just saying Butcher, maybe it's Butcher spelled differently. The chemistry of splitting water is the easy part. It was first done by English scientists more than 230 years ago. By the 1890s, engineers in France had built an electrolysis plant to produce hydrogen for military airships. A few decades after that, hundreds of such plants, mostly powered by hydroelectric dams, were producing hydrogen to make ammonia fertilizer. So that became a savior in terms of green revolution and feeding the ever-growing population and so on. But with the advent of steam methane reforming in the 1930s, the cost of making hydrogen plummeted. Green hydrogen was replaced with gray. Oops, I screwed up something here. Let me just hold on a second. Okay, I'm gonna pause it. Sorry about that. I had replaced some text, so let's get back. So we were talking about the chemistry of splitting water and how prices dropped for gray hydrogen of producing it from methane reforming. Today, multiple electrolyzer technologies are vying to turn the hydrogen market green again. The most common and commercially mature version is known as an alkaline water electrolyzer, AWE. Nice acronym, right? It works a bit like a battery. Two electrodes separated by a porous membrane are immersed in water containing an electrolyte that encourages the movement of ions, exactly like a battery. Well, in a battery, you produce ions and keep them separated, and the wire then flows, ions flow and give us electricity. Green electricity fed to the negatively charged cathode splits water molecules into hydrogen molecules and negatively charged hydroxide ions, OH minus. The hydroxide ions are drawn through the membrane to the positively charged anode, where they react to form oxygen and a small amount of water. The membrane slows the commingling of the hydrogen and oxygen, which would otherwise combine explosively. Dozens of such cells are stacked side by side to create an overall electrolyzer. And O's main advantage is that the catalysts that coat the electrodes to speed up the water splitting can be cheap, such as nickel and stainless steel, but the approach has limitations. If the supplied currents drops sharply, as can happen with intermittent renewable energy sources, extra hydrogen can diffuse across the membrane to the oxygen producing anode, creating an explosion hazard. Another problem, an AWE's electrode electrodes typically can only handle relatively small currents. That means the electrodes must be large and, despite the cheap catalysts, costly to make significant amounts of hydrogen. Now, some good engineering problems there. Innovative tweaks could help. In a standard OS, for example, the produced gases tend to form bubbles on the electrodes, which impede the splitting of additional water molecules. But in 2022, Gerhard Swigers, a chemist at the University of Wollongong, and his colleagues came up with a new design that relies on a membrane with a capillary design that wicks water and electrolyte from the bottom of the cell up to the electrodes on either side. Because the electrodes aren't submerged in liquid, bubbles are no longer a concern. The design allows the gases to be shunted off as soon as they are produced, reducing the risk of explosion. Okay, so good solution. Swigger co-founded the startup Hisata, which has built lab-scale prototypes that demonstrate the superior efficiency of the capillary membranes. Whereas most OS require 50 to 53 kilowatt hours of electricity to produce 1 kilogram of hydrogen, Hisata devices only need 41.5 kilowatt hours, already beating an efficiency goal set for 2050 by the International Renewable Energy Agency. Okay, that is IRENA. This is a giant leap in performance, says Hisata's CEO Paul Barrett. In May 2024, the company announced it had raised $111 million to scale up the technology. Okay, if the alkaline cell is the current king of electrolyzer technology, then proton exchange membrane (PEM) is the teenage challenger. In PEM cells, the action is reversed, beginning not at the cathode but at the anode, which pulls electrons off water molecules to split them into oxygen molecules and protons. The protons travel through the membrane to the cathode, where they meet up with the electrons supplied by the renewable electricity to create hydrogen molecules. Okay, slightly going in the reverse direction, but basically you still need energy. Here is the unlocking of green energy. This is the electrolyzers that can be used that can use green electricity to split water molecules into oxygen and hydrogen gas. All three major designs resemble a battery with a pair of electrodes separated by a membrane. You typically have an electrolyte in a battery, which allows the ions to get back. They can be expensive to build and inefficient, requiring 50 to 60 kilowatt hours of electricity per kilogram of hydrogen. Three main types of the electrolyzers are vying to boost efficiency and lower cost. So here is the renewable electricity, and there is the hydrogen tank, which is going to store once the electrolysis chamber does its work, and here is the electrolysis cell section. So you have alkaline water electrolyzer that we talked about, or that has been around for more than a century, but commercial interest has prompted recent improvements. And the pros here: mature technology, cheap catalysts, low capital costs, and the cons are moderate efficiency, therefore large, can produce explosive gas mixtures, don't work well with fluctuating currents, and renewables typically are now fluctuating. Of course, one can use batteries and so on, but life cycle still has to make it affordable. So here is a cathode, a porous separator, and an anode, and here is oxygen being pulled out to avoid any explosion. Water gets split. Nickel and steel catalysts are working to split the water and give you OH minus and H2 plus. So H2 plus has to be moved away, kept very separate from the oxygen to avoid explosions. The proton exchange membrane (PEM), also decades old. PEM devices send ions in the opposite direction from Oz. So instead of going this way, they'll be approximately going this way, as we'll see in a minute, across a solid rather than a porous membrane. The pros: higher efficiency, therefore they can be smaller, work better with fluctuating current, so that takes care of the renewable energy use, work better with high currents. And cons are that typically requires costly iridium catalyst as opposed to the cheap steel and so on. Membranes used for ever chemicals, which we don't want to release into the atmosphere or ground or water and so on, often higher capital costs. So here you have water, and oxygen is being pulled out here. Here is the anode, and it's sending off H plus to the cathode, and there is a solid membrane that separates the two, and you have iridium catalyst here, which then takes the H plus and produces the H2 for you to go out this way. So this is separating the O2 and H2 more effectively than the production of explosive mix here. So anion exchange membrane is another way of doing it. So here you have an anode, again a solid membrane, again you are producing H2O coming in and producing OH minus, and here is H2 going out, but this is a nickel based catalyst. And what is the difference? The difference here is that latest technology, the anode exchange membrane, combines features of both older designs and could lower costs, but it still must prove durable for decades. So it's time to go. I mean, in terms of making it technology ready. The pros are that it doesn't require iridium, efficiency could be high, no forever chemicals are released, and cons are rapid membrane degradation happens because of the way it works, may degrade with fluctuating currents, and high current operations unproven. Okay, so let's read that a bit. The key difference from Oz is the membrane. It isn't porous separator. It isn't a porous separator, but a dense solid polymer made up of spaghetti-like molecules with chemical appendages that readily transfer protons across the membrane like a bucket brigade. The membrane requires no liquid electrolyte and reduces hydrogen crossover. On top of all that, PEM designs can typically handle larger and more variable currents that translates to smaller, potentially cheaper electrolyzers that can produce the same amount of hydrogen. But PEM electrolyzers can also have their downsides. Higher electrical power ravages most metal catalysts. Further corrosion comes from the protons, which create highly acidic hotspots. To withstand these conditions, PEM electrodes are coated in durable catalysts made with iridium, an extremely rare metal that's twice as costly as gold. There is not sufficient iridium to grow the industry, says Pelayo Garcia, the Arquer, an electrolyzer expert at the Institute of Photonic Sciences, ICFO, in Barcelona, Spain. To make matters worse, the membranes are typically made from fluoropolymers, so-called PFAS materials that persist in the environment forever chemicals and are being phased out in many countries. So you don't want to bring a new way of producing renewable energy that's going to increase that in any way. Many groups are devising novel PM membranes without fluorine, as well as electrodes that require less iridium. PM cells usually rely on iridium oxide, but recent theoretical work suggests the iridium in another compound, IRO3, is more reactive, potentially allowing chemists to use smaller quantities. Ryuichi Nakamura and his colleagues at the Riken Center for Sustainable Resource Science synthesized IRO3 and sprinkled that on top of a manganese oxide electrode coating using just 4% of the iridium normally needed for PM devices, so 96% reduction there. That's good news. The electrolyzer churned out hydrogen at essentially the same rate at the top IRO2 devices with no signs of degradation for more than 30,000 hours. And the team reported last year in Science these results. We are also already working with companies to scale this up, Nakamura says. Obviously, these people tend to be very gung-ho. they raise capital and they want to corner the market, etc. So you have to always wait for those things to be at scale. Other PEM researchers are looking to increase the durability and catalytic efficiency of cheaper metals such as cobalt and tungsten, hoping to replace iridium altogether. In June 2024, Garcia and his colleagues reported that pre-treating a cobalt tungsten catalyst in a basic solution helped shield it from acidic degradation and stabilized the metals in a more catalytically active arrangement. The upshot, the catalyst's output jumped fivefold to nearly that of iridium dioxide, and without iridium, we have the highest current density and highest stability for non-iridium catalysts, says co-author Lou Xia at the ICFO. Bocher calls the results quite remarkable, but notes the researchers still need to show the alternative catalysts can match iridium's ability to handle high electrical currents, which is needed for efficient electrolysis. Both the cobalt tungsten catalyst and Riken's IRO3 version still have a lot to prove. To be commercially viable, water splitting electrodes need to last about 10 years, and neither catalyst has been tested for more than a few months. There could be some pixie dust that comes along, and this may be it. Just pixie dust miracle. Basically, Swigert says of the new options in this way, there could be some pixie dust that comes along, and this may be it, in terms of cobalt tungsten catalyst. But for now, iridium seems to be the only material that works long term with PEM, with all its cons in terms of forever chemicals. Long-term durability is also the main challenge for the third kind of water splitter, anion exchange membrane or AEM electrolyzers. These emerging devices attempt to blend the best features of O and PEM designs. Like Oz, they ferry hydroxide ions produced at the cathode through a membrane to the anode, and they do not need precious metal catalysts or a fluorine-based membrane. But like PEM devices, AEMs use solid membranes designed to conduct hydroxide ions rather than protons. The combination could make them cheaper and able to handle the variable electricity supply from the renewables. The problem is that the oxygen-forming catalysts at the anode also promote reactions that chew through the membranes, causing them to break down in weeks or months, says Paul Kempler, a chemical engineer at the University of Oregon. But many labs are exploring ways to boost membrane durability. Germany-based Enapter, for example, spikes the water with liquid electrolyte, creating an environment that prevents corrosion. Enapter CEO Jürgen Lachmann believes the tweak will enable membranes to last for a decade. Our stacks will last as long as other stacks, he predicts. Bocher's group has its own strategy for protecting the membrane, coating the anode with a thin layer of hafnium oxide. The coating allows hydroxide ions passing through the membrane to reach the anode, but because it's an insulator, it blocks the electrical charges that tear apart the membrane. In the 16th February 2024 issue of ACS Energy Letters, Bocher's team reported the hafnium oxide layer dramatically slowed membrane degradation. He calls the results preliminary, but says that if the strategy works on a commercial scale, this is a home run technology. Coming to green hydrogen, we'll need multiple home runs like this. Perhaps the biggest challenge the industry faces is the price of electricity, which makes up roughly 2/3 of the cost of green hydrogen, says Brian Pivovar, who heads electrolyzer research at U.S. National Renewable Energy Laboratory. Without subsidies, a price of $1 per kilogram of green hydrogen is impossible at today's electricity prices, no matter how cheap the electrolyzers get. Pivovar says to reach $1 per kilogram, renewable electricity costs will need to fall by a factor of 10, according to a DOE green hydrogen roadmap. We are reliant on the solar, wind, and utility industries to get the price of electricity down. So on the technical side, you are worrying about anodes, corrosion, forever chemicals, the cheap catalysts, and so on. On the other hand, you are worrying about energy costs as well. Green hydrogen need not be the only cheap Green hydrogen needs not only cheap electricity but heaps more of it. The DOE roadmap says meeting a US target of producing 30 million tons by 2030 will require installing some 200 gigawatts of fresh renewable energy capacity, nearly double the installed US solar capacity today. Okay, coming closer, even if all that happens and green hydrogen starts to be copiously produced, manufacturers will face the challenge of storing it and shipping it to customers. For existing hydrogen users, such as oil refineries, shipping and storage already adds at least $2 per kilogram to the cost of the gas, according to a December 2024 analysis in Joule by Harvard University's Roxana Shafi and Daniel Schrag. So unless those costs drop as well, or green hydrogen factories can be located close to customers, prospects for ubiquitous green hydrogen are dim. Hydrogen may be the best way to decarbonize some sectors of the economy, Schrag says, but it's a lot more expensive than people are portraying. For now, all those realities help explain why Sohical is only bubbling out enough hydrogen to fuel 2 city buses, but Harris believes green hydrogen has momentum now. His company is already inked an agreement to launch a similar demonstration facility in Michigan this year and has 6 other US plants on the drawing board. Green hydrogen is not a commodity yet, Harris says, but he thinks it's finally here to stay. Okay, so I read these things because even though I'm not an expert, I learn a lot by reading them and then reporting to you. Plus, we need to be aware of these because as climate scientists, we worry about predictions, projections, early warnings, but we need to track all the potential solutions that are on the horizon as well. So even if we don't understand all the details, we just can read and just be aware of what all is going on and what are the issues they are facing and how things will work out as we keep making up things about safe global warming targets and so on and so forth. Okay, so see you in the next topic.